Alright, so welcome back. In the last video, part 2 of this series, we described the apparatus for this fluid pressure lab. Now what we'll do is just run through the steps required to perform the lab. So just as a review, so we have this cylinder which will be the floating object, and we have the vase full of fluid. In this case we're using water, but you could use some other fluid. We have an alignment fixture that will go in the vase, and then we have a series of masses, or weights if you will, along with a hanger that will go inside the floating object, the cylinder, to be able to give you a variety of weights when you collect data. So if you would like to get a copy of the worksheets for this lab, you can just send me an email. I'll include the email in the video description that goes along with this video. And just send me an email and I can send you a copy. Alright, so as we get started here, there are 2 measurements we need to take to get started, and then we can start showing how the calculations are performed. So one calculation is going to be the diameter of the cylinder, because we're going to be calculating pressure exerted by the cylinder on the fluid in the vase. So we need the cross-sectional area at the bottom of the cylinder. So I'm going to use dial calipers. You can use other measuring instruments. I like the dial calipers because it measures the round cross-section very well, and it'll give you a measurement out to 3 decimal places. Okay, and this measurement is 1.577 inches. And then the other measurement we need to take is, let's measure the mass of the cylinder with the smallest amount of weight added to it. So we have this mass hanger, and the bottom of the mass hanger itself has about the same mass, maybe a little more than the other ones that we're going to add later. So what we'll do is place this mass inside the cylinder, place it on the scale, and I'm going to measure in grams. This is 160.3 grams, and we'll convert that to pounds here in just a minute. So let's continue now with the worksheet. So you can see now on our worksheet we've entered the cylinder diameter that we measured at 1.577 in inch units, and then we'll use that to calculate the cross-sectional area of that cylinder, which is the floating object. So it's a round cross-section, area equals pi r squared, and if you do that calculation, then you end up with 1.953 square inches. Just a note about significant figures. If you're electing to track and use significant figures during your labs, then remember that significant figures are based on how many significant figures are in the measurement. So in this case, the cylinder diameter measured at 1.577, which is 4 significant figures. So I'm going to express the cross-sectional area in 4 significant figures. So that's up to you whether you expect significant figures to be expressed. Sometimes if there's too much focus on significant figures, sometimes the students will lose track of what the real purpose of the lab was. So sometimes I ask for significant figures to be expressed properly. Sometimes it does seem to get in the way. Anyway, so cross-sectional area 1.953, and you've also recorded here the mass of the floating object, which we measured on the scale as 160.3 grams. Now there are some conversions you'll need in this lab. The conversion from grams to pounds, which we're going to use here in just a minute. Conversion between inches and centimeters, cubic feet and cubic inches, and then also you'll need a density. In this case, the fluid I'm using is just plain water, 62.4 pounds per cubic feet. If you elect to use some other fluid like alcohol or some other fluid, you'll need the density of that fluid. All right, so I've set up this lab to be expressed in English units. So we're going to convert the grams to pounds using the conversion 454 grams to a pound. And if you do that, then the weight of the floating object is 0.3531 of a pound, again expressed in 4 significant figures. And you'll also notice that the mass from our scale was also in 4 significant figures. Okay. So as we saw in the previous videos in this series, that if the cylinder is pushing down on the fluid with a weight of 0.3531 of a pound, which is a force, then the buoyant force of the fluid pushing up on the cylinder is the same. We're assuming this is just an equilibrium situation. And using that buoyant force and the cross-sectional area of the cylinder, we can calculate the fluid pressure at the bottom of the cylinder, which is force divided by area. So that will be the 0.3531 divided by the area, which was the 1.953 square inches, and that calculation will give you .01808 pounds per square inch. Okay. So then what you can do is now you can make a prediction before we actually put the floating object in the fluid. You can make a prediction. Well, how deep should it be? And so you use the fluid pressure equation. Pressure equals density times depth, which is H. Solve for H. Pressure divided by depth, by density. Now this calculation will look something like this. The pressure being the 0.1808 pounds per square inch divided by the density, 62.4 pounds per cubic feet. So you see you need a conversion. So you'll need to throw in a conversion of between cubic feet and cubic inches, and then you'll get a result in actual inches. So in this case it ends up being 5.007, just a little more than 5 inches. Okay, so now what we're going to do is we're actually going to collect the actual depth data, the actual depth of the cylinder, by placing it in the water and measuring the depth. So let's set up our apparatus. Now you have to make sure the water level is appropriate, that it can accommodate all of the weights that you're going to place in the cylinder. You could end up starting with a water level too high and you'll get water coming out the top. All right, Alright, so here's our floating object, and reading the tape on the side of the cylinder, it looks like 12.9 centimeters. Okay. And when you take further data on other weights, then you would just have to take one of your other weights, make sure you then weigh the whole object before you place it in. And this one's a little deeper. This is more out around 15 centimeters. But let's just focus on that first measurement that we had. Now let's keep going on the worksheet. So we measured the object depth within the fluid, 12.9 centimeters. So what you'll do now is do a conversion from centimeters over to inches. We measured in centimeters because my measuring tape on the cylinder is calibrated in centimeters and millimeters. So if you do that conversion between inches and centimeters, you'll get 5.08. I'm expressing now in 3 significant figures because the measurement was in 3 significant figures. And the last step here then is to measure the actual fluid pressure. So this is the actual depth in centimeters and then in inches, and now we can calculate the actual fluid pressure using pressure as density times h, which is the depth. And then once again, as we did earlier, you'll have to include a conversion between cubic feet and cubic inches. And if you do that calculation, you'll get 0.183 pound per square inch for fluid pressure. And then what you'll do is the same exercise for a variety of different weights. This table just has room for 5 different weights of the floating object. Same calculations. And then the next step that we'll cover will be the graphing. There's a graph where the data can be graphed, and then you can do a calculation of the density of the fluid and see if it makes sense and reflects that we were indeed using water. Okay, so now we're going to return to the graphing portion. Hopefully you can see that okay. Okay, so we have a graph now. Vertical axis, pressure in pounds per square inch. Horizontal axis, the measured depth, h, in inches, taken off our worksheet. I demonstrated the very first data point and the calculations, and I've gone ahead and done the other 4, so we have 5 data points. So what's being graphed here is the actual fluid pressure and the actual depth, which were the 2 columns on the furthest right on the worksheet. And I've gone ahead and with a clear straight edge drawn a best fit line, and so now what we're going to do is calculate the slope of this line on the graph. So using the fluid pressure equation, so we know fluid pressure is density times depth, and if we solve this equation for density, that's equal to fluid pressure divided by depth, and that's what you're seeing on this graph. We're graphing fluid pressure versus the depth. So you remember that the slope of a line is equal to rise over run, and in this case the rise is pressure, fluid pressure, the run is depth. So if we calculate the slope of the line, we'll calculate pressure divided by depth, which we see from the fluid pressure equation is density. So we should get a result here of something close to the 62.4 pounds per cubic feet. So I'm going to use 2 points that look like they're well placed on the line, point 2, point 1, and we'll use the mathematical equation slope is y2 minus y1 over x2 minus x1. And if we do this calculation, well, I can go ahead and give you the data points here. The slope then would be equal to, this is 0.277 minus 0.213 divided by 7.68 minus 5.91. And on the run, those were the actual measured depths in inches for those other weights. And then you also have to apply, of course, the conversion between cubic feet and cubic inches. And when I calculate that, I end up with 62.5 pounds per cubic feet, which is very close to the density of water. So this is just an interesting exercise in graphing and interpreting a graph and making sense out of it. And also is a good check on the execution of the lab. If you got a result that's wildly different from the actual density of water, you'll have to go back and figure out what didn't go well. All right, hope this is helpful.